So we have some pictures that will help with all of these trends to give you a visual. We can just tell you what's going on, but how is that fun, right? So we will summarize what's going on, but we have a few different trends. The first trend, and this is really important because we do chemistry, like there's reasons behind why atoms will form certain shapes. They have to be of a certain size to put enough things around them. So like a basketball could fit a whole lot of ping pong balls around it, but a ping pong ball could not fit a lot of basketballs around it. So size plays a role in what kind of bonding can happen. It also plays a role in how many electrons are available to do sharing. The larger an atom gets, the less they notice if there's a electron way out, like their 72nd electron goes missing. They don't quite notice as much as, maybe something that only has 3 electrons is going to notice it. So size plays a role in the kind of chemistry that things will do. So let's look at size and what's going on. You can tell in this first picture, if these little spheres represent atoms, you can definitely tell that this side of the chart over here is where you have the large atoms. So I'm going to make this like a triangle here. So this is where you have large atoms. And again, if you think of the effect of nuclear charge, as we're going in this direction, you can see all of these get smaller because there's more protons pulling on their electrons. And hopefully what you're seeing is that there's a directionality to this. Over from this direction of the chart, going in that direction, that's where you get to the large atoms, and over here is where you're at the small atoms. Notice that even though fluorine has more electrons and more protons than lithium, he's still smaller. So we're talking about that distance from the nucleus to the outermost place that electron can get to. So remember, the electrons are constantly moving, and they're constantly in this one shape. So if you measure the distance like to the farthest it could go, and again, if you're imagining that the nucleus is spherical, say this is the farthest point out that electron in an s orbital could go, that distance is their radius. So a large atom would have a large radius, and that implies a large size, and a small atom has a small radius. So this is our trend. This is another way we represent trends are with these vertical columns, and you can see these are like really close to about the same size. And again, that this is really, really, really small. Let's make sure you understand this is about size. These are all neutral, by the way. In this picture, we're talking about neutral atoms. As you go across, the radius gets smaller. So across to the right, the radius gets smaller as the effective nuclear charge gets larger. The core electrons are pulled into the nucleus. The valence electrons are pulled into the nucleus, which allows all the electrons to be pulled in close to the nucleus. Well, the cores and the valence are getting pulled in. This makes the atom smaller. All right. So let's look at where fluorine, carbon, and lithium are. So here we go. Fluorine is right here. Here's carbon, and here's lithium. So maybe you're looking, you're like, I can tell fluorine is small, carbon looks small, I think, but those are kind of far apart. Just follow the trend. So how we make this arrow is the elements most this way and most this way. That's like how we get in this direction. So what I like to do, because I'm not a big arrows person, is I like to just count squares until I can get to that part of the chart. So for example, this would be like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It'd be like 10 squares to get there. Whereas like here, 1, 2, 3, 4, that's only 4 squares. Or like in 1, 2, 3, 4, 5, 6. See how that's more squares? So sometimes that's how I do it. I just count squares to get over to where I know the large elements are. So this is the largest, and fluorine is the smallest. And then we're going to compare sodium, rubidium, and cesium. And again, it goes in that direction. Sodium is smaller than rubidium, which is smaller than cesium. Generally, transition metals only change a small amount within the same row. Very, very small amount. It's hard to measure within the D block. So this trend is most effective like on this side and this side. And although these kind of look like they're going up, there's not that much. There's just some difference. So there's not a huge change. So just be aware that the change within the transition metals, you probably won't be given transition metals for this trend because the change is just so very slight, like especially in this range there. Also note, you don't have to know the trend for reactivity or metallic character, but it is in this exact same direction. So this These are the most metallic atoms, and they are also the most reactive atoms. If you look up videos and see lithium, sodium, and potassium reacting with water, they will become increasingly active when you put them in the water.